Good morning. My name is Brendan McGinty, and I'm part of the Center for AI Innovation at NCSA, National Center for Supercomputing Applications at the University of Illinois Urbana-Champaign. Happy to have you here for another seminar over the lunch or so hour, and we are extremely pleased to have Dr. Zhizhen Zhao with us today. I'm going to introduce her in just a second, but as a reminder, after the presentation, we'll have time hopefully for a few questions. If you want to enter them for me to ask, please enter them in the chat, but I will certainly open up so that you can ask directly at the end as well. And the presentation is being recorded and will be posted on our website typically a few days after the presentation happens, so hopefully near the end of this week. So without further ado, I would like to introduce Dr. Zhao. Dr. Zhizhen Zhao is an assistant professor in the Department of Electrical and Computer Engineering at the University of Illinois Urbana-Champaign, with affiliation to the Coordinated Science Laboratory and the National Center for Supercomputing Applications. She's also an affiliate assistant professor in the Department of Mathematics and the Department of Statistics. Prior to joining the Electrical and Computer Engineering Department at Illinois in 2016, she was a current instructor at the Current Institute of Mathematical Sciences at New York University. She received her PhD in physics from Princeton University in 2013, working with Amit Singer, and graduated from Trinity College, Cambridge University, with bachelor's and master's degrees in physics in 2008. Dr. Zhao, we are so happy to have you with us today. Go ahead and take it away. Thank you.
Oh, thanks a lot. Yeah, thanks a lot for the introduction and invitation. Yeah, so today I want to talk about the machine learning and inverse problems in scientific imaging. So here is the plan for today's talk. So I'm going to talk about two works that are happening in my group. One is the adversarial learning for unknown view tomography. The other one is the cryo-electron microscopy image denoising. So these are the joint work with my students, Mona Zekny and Yifeng Fan. So we know that imaging are now widely used to characterize physical, material, and chemical and biological processes. So for example, in cryo-electron microscopy is widely used to determine the 3D shape of macromolecules. So for example, experimentalists prepare hundreds of thousands of samples, fast frozen in very thin ice layer, and then they image it in the electron microscope. You collect the micrograph, and through single particle analysis, you can get this 3D density map. So from the 3D density map, people try to resolve the atomic model. And also the other example is that, say, the X-ray free electron laser. So they inject the particle samples into this laser beams, and then they collect those diffraction patterns through all different orientations. The benefit of that is that you can see the molecular movies of the chemical reactions. So there are a lot of challenges in handling the imaging data for those scientific applications. So we will face, for example, measurement uncertainty. So for example, we have noise due to the low dose imaging in cryo-EM or in the X-ray free electron laser experiments. And also we have unknown latent variables. So for example, in cryo-EM, when you freeze the samples, you don't know how they orient in the thin ice layer. And also for the X-ray free electron laser, when you inject the particles into the laser beam, you also don't know, you can't control the orientations of the particles. So these are the latent variables that can affect your observations. In addition, we also have incomplete data. So for single measurements, we only have a partial view of the underlying, let's say, image or underlying 3D object. So the question is, how can we combine different observations together to reconstruct the underlying structure? So the corresponding inverse problems involves how do we do the denoising, 3D reconstruction, or estimate the physical or chemical process parameters. So to apply machine learning into the scientific imaging, we need to incorporate the physics-based image process. And also we want to understand the geometric and statistical properties of the data. So in this talk, I'm going to focus on two examples. The first one is the unknown view tomography, and then the second one is on the image denoising for cryo-EM. So for the first part, let's look at using adversarial learning for unknown view tomography. So what is the unknown view tomography? So the basic idea is the following. So here I provide the illustration of the 2D tomographic reconstruction problem. So we have a set of 1D projections. Each of them correspond to the line integral of the intensity of this 2D image along certain viewing directions. So for example, in this direction, we have the plane projection illustrated in blue. That's basically taking the line integral of the 2D density through this direction. So the forward model for those measurements is the following. So we have a linear operator, P, parameterized by theta, and then it's applied to the underlying 2D image. And the resulting measurement is corrupted by, let's say, additive white Gaussian noise indicated by this epsilon subscript L. The linear operator, note here, is parameterized by this viewing direction theta L. And we assume that this is drawn from some underlying distribution of the viewing angle. So if the viewing angles theta L are all known, so for all the measurements, we know accurately what are the measurement angles, then the corresponding inverse problem is a linear inverse problem. So there are many existing methods that can help you reconstruct the underlying 2D image. However, the problem gets more challenging if theta L is unknown. And in addition, if we don't really know the distribution of the theta angle. So now when theta L and I are jointly unknown, the corresponding inverse problem is nonlinear. So for the unknown view tomography, we basically want to recover both the image I and in our work, we basically try to recover P theta instead of the individual theta L's, given the unordered measurement data CL, for L is from 1 to capital L. So here, basically, you can think about you have a bag of all those 1D projection profiles, and then you want to figure out what are the underlying 2D image. So there are many existing works on solving the unknown view tomography. Here, I give you an incomplete list of different kinds of methods. So the first approach is essentially focusing on recovering the viewing angle for each individual measurement. So earlier, people have done a lot of analysis of the uniqueness and feasibility of tomography and with unknown view angles. And later, people have designed algorithms called graph Laplacian tomography to recover the underlying 2D image from those random projection views. And also people try to use the moment-based method to infer the angular difference for any pairs of measurements. So overall, those methods rely on basically doing pairwise comparison of your measurement data, measured projections, and then try to infer what is the underlying angle associated with each individual measurement. And once you figure out the angles, then you can directly apply the traditional tomographic reconstruction to get the 2D image. The second type of the measurement relies on using the maximum likelihood estimation or MAP estimation. So you can treat those methods as a fuzzy assignment of the viewing angles. So for each measurement, you can define the association of different views with different weights based on the likelihood. So for this kind of approach, you still try to estimate the views for each individual measurement. More recently, people start to look at other alternatives. So for example, for the 3D problem, Gupta et al. Recently proposed a method called cryo-EM, which is using a generative adversarial net to recover the underlying 3D object from the 2D projections from unknown viewing angles. In their framework, they assume that the underlying viewing distribution is known and is given. Then they use a GAN structure to reconstruct the underlying 3D object. So later we followed up that work, but apply it to the 2D unknown view tomography. In addition, we in this work for the UV tomoGAN, we don't assume that we know the distribution of the viewing angles, and we try to jointly recover the viewing angles and the underlying image. Okay, so the idea of using this comparing the so for the last approach that we mentioned for the generative adversarial learning-based approach, the basic idea is to compare the distributions of your measurement data and your model simulated data. So just to illustrate, so here we basically have those blue stars, which you can think about, these are data points in high dimensional space, let's say RD. And these are the set of all our measurement data in RD, and we call it P data. Then what we want to do is we want to infer from this set of data the underlying parameters that generated such data distribution. So we know that the parameters that control this data distribution are the corresponding underlying 2D image and the distribution of the viewing angles. So we can basically initialize the I and P theta, and then we can, based on those parameters, we can simulate our measurements. So the red crosses are the simulated data based on our underlying parameters I and P. So we call it the model distribution parameterized by our 2D image and the viewing angle distribution. So now we can compare the distributions from our measurement data in blue stars and our model distribution in red crosses. So we can compare them based on some kind of divergence or distance between those distributions. Right? Based on the distance of those, the data distribution and the model distribution, we can update our initial guess of our parameters I and P theta. So in summary, we can have basically the statistical inference is performed by minimizing over the parameter space the distance or divergence between model distribution and the empirical distribution of the data. So there are many choices for how we compare the distance or divergence between distributions. So for example, we can use CAII divergence, Jensen-Shannon divergence, or total variation, etc. And here I want to also mention that the CAII divergence is closely related to the maximum likelihood estimation. But here instead, we want to use the Earth mover's distance or the Wasserstein-1 distance. So informally, if the distributions are interpreted as two different ways of piling up a certain amount of dirt over some region, then the Earth mover's distance is the minimum cost of turning one pile into the other, where the cost is assumed to be the amount of dirt moved times the distance by which it is moved. So instead of using the original definition of the Earth mover's distance, we use the Kantorovich-Rubinstein duality for evaluating this distance. So essentially, it is trying to find the function in all one Lipschitz continuous one Lipschitz functions that maximizes the difference between the expectation of f of x, where x is drawn from the distribution of the data, whereas the other x is drawn from the model distribution, right? So in the Wasserstein GAN, the Wasserstein generative adversarial network, essentially we use a network to parameterize this function f and try to find what is the corresponding f that gives us an approximation of the Earth mover's distance. So this part that parameterizes this f is usually called the discriminator or critique. So compared to KL divergence, the Earth mover's distance is more suitable in learning distributions supported on lower dimensional manifold. That is because if two distributions are very well separated, the KL divergence or Jensen-Shannon divergence cannot really provide useful gradient information. Okay, so that is so previous slide was basically telling us what's the motivation of using the distribution matching or for solving this inverse problem. Now, getting back to this image related application, we also have some assumptions on the images. So here I'm showing you an image we simulated through projection of a ribosome data into 2D. So we can see that the object in real domain on the left, so on the left, I'm showing you a plot in the real space. So you can see that the object is well supported or very concentrated in the real domain within radius r. And on the right, I'm plotting the absolute value of the Fourier coefficients in log scale. And you can also see that this should be basically band limited with some band limit C. So basically, we assume that the function that we try to recover in terms of the 2D image is essentially a band limited function which is concentrated in real space. So therefore, we want to kind of find an efficient representation of the image that we try to recover. So the idea is to use this Fourier-Bessel basis, which is of the following form. On the angular direction, we have the Fourier modes, e to the ik theta. And on the radial direction, we have the Bessel function. And here, the important part is to note this Bessel locations of the Bessel zeros, r subscript kq. And q is an index of, let's say, the qth root of the Bessel function jk. And outside of this radius c, basically this function is all zeros. So this forms a basis for a disk of radius c. Now, for any image, we can basically say take the Fourier transform of that image, and it can be expanded on the basis function. And using q is from 1 to infinity, k is from minus infinity to infinity. However, in practice, when we do the computation, we need to truncate it. So what is the criterion for us to truncate such expansion? So the idea is, now if we look at the inverse Fourier transform of this basis function, we have an analytical expression, which is of the following form. And you can see that in the denominator, we have 2 pi cr minus r squared kq. And on the numerator, we have this jk 2 pi cr. And we notice that if we have k is equal to 10, q is equal to 1, we plot out the amplitude of this function. Then this looks like an annulus in this 2D. And if we increase q from 1 to, let's say, 16, and you can see that the radius gets larger. And if we further increase q, you can see that this bright annulus gets, the radius gets even larger. So the sampling criterion is saying that I don't want this radius to be outside of, to be too large, such that I pick some redundant, or we don't pick any useful information that is related to the object. So therefore, the criterion of that is essentially the location of the Bessel zeros, rkq plus 1, has to be smaller or equal to 2 pi cr. So then using this sampling criterion, we can have the following truncated expansion, meaning that the image in 2D can be written as the expansion coefficients times this inverse Fourier transform of the basis function, where basis is chosen such that the angular frequency is bounded between minus k max and k max, and q is from 1 to pk. Okay, so this is why that we want to use a different basis function to represent our images. So, and for tomography, we also need to use another property, which is the central slice theorem, or sometimes people call it Fourier slice theorem. And instead of working with the Fourier domain, we use the real version of the Fourier transform, which is the Hartley transform. So the basic idea is that if you do a 1D Fourier transform of the projection line, that's indicated, or Hartley transform of the projection, that's indicated as the Xi tilde, that corresponds to the Hartley transform or Fourier transform of the 2D image, and that corresponds to the central line. So meaning that you have you do the Hartley or Fourier transform of the image, and they take the line at the angle theta L, that should be equal to the Fourier transform or Hartley transform of your measured projection line. Okay, so using this property, we can see that the truncated expansion of the Hartley transform image on the Hartley-Bessel basis. So here, instead of using Fourier-Bessel, I'm using the real version, which is equivalent to Hartley-Bessel basis. Then we can represent the image using this expansion coefficient, let's say CKQ. So the benefit of using this representation instead of the original pixel domain, now we work with the expansion coefficients, is to regularize that the image is concentrated in both the frequency and the space domain. So therefore, using this transform, we can rewrite our forward model in the transform domain as the following. So here still we have a linear operator given theta L times this expansion coefficients plus noise. So with those two ingredients, one is the measure the difference in the distribution and also represent the image and projections in a different domain. Now, here is the main diagram for our adversarial learning-based reconstruction. So essentially for an image, it can be represented by its expansion coefficient C, indexed by K and Q. And also we have the viewing angle distribution P of theta. So in the green box, this is our measurement data. We take our measurement data and do a Hartley transform. So we have the zeta tilde, and these are the Hartley transformed data. So we pass this through our discriminator. Basically, that is helping our critique or discriminator to learn the distribution. And on the generator side, instead of using a network to parameterize the image, we basically input the physical model for our imaging problem. So it's the tomographic projection. We have this forward model where theta is drawn from this underlying distribution P. Okay, so once we pass through the discriminator, we can also use the gradients of the loss to update our parameter C and P. Okay. So now follow the Wasserstein-Gann, the loss is of the following form, right? So here d phi is kind of the network parameterized function of f in our previous discussion of the Earth mover's distance. And then we also apply this gradient penalty term, which regularizes that the discriminator function is 1 Lipschitz. Okay, so here, in training this part, we basically maximize the loss with respect to phi and minimize the loss with respect to C and P. If we focus on the generator loss that is associated with our expansion coefficient C and the distribution, angular distribution, then we can see this is actually of the following form. So we basically sample theta B and then So this is our generated measurement, and we pass it through our discriminator. We can also rewrite it as putting a delta function centered at theta b. And so this is basically our generator loss function. So the generator loss function, if we look at it, since we do the sampling theta b from p, so this is not directly differentiable with respect to p. Since we need to actually estimate both c and p, so the question is, how can we allow the backpropagation through p? So the basic idea is the following. So we first discretize our projection angle domain into n theta equal bins, and then we use the gumbo softmax to allow backpropagation through samples from the discrete distributions. Right. So then using this gumbo softmax, we can approximate LG such that it is differentiable in both C and P. So what is gumbo softmax? So we know that the gumbo max trick provides a simple and effective way to draw samples from a categorical or discrete distribution with probability P. So here, G subscript BI is drawn from a gumbo distribution. And the sampling is through taking the argmax of this quantity GBI plus log P of I. So here P is your underlying distribution. But we know in argmax is non-differentiable. So the alternative is to use a softmax function as a continuous and differentiable approximation of argmax. So therefore we can now write it as RIBP, which is so this is the softmax term instead of the argmax. So now with this RIBP, now we can rewrite our generator loss in terms of the function RIB of P, and then the discriminator part of this form. So after this modification, we can see that the loss is now differentiable with respect to both P and C. So this is our overall modification with respect to the previous cryo-GAN structure, where we basically add this line, this part that allows it to be differentiable with respect to P. So here I show you some results. So here the first one is based on clean measurement data, and I want to show you the reconstruction through the iterations. So let's say we can see that through the iterations, our reconstruction results gets better. And also in the second row, we are comparing our recovered distribution in red with respect to the original distribution that samples draw the angles from. And also the blue ones are the sample distribution. Here we have the measurement contains 2,000 projections. So you can see that the blue line is a little bit noisy compared to the green line. And we can see that the red curve basically fits the green curve when the training converges. So here we also have some numerical results for the reconstruction using the clean data, where we have the first column is the ground truth 2D images. For the first two rows, we are using the methods that rely on estimating the individual viewing angles from pairwise comparison. So the first column is using the graph Laplacian tomography. And then the second column is using the MATE, so using moments-based method to estimate the angular difference between projection 1D projections, and using the graph Laplacian to get a better estimation of the angles. So we can see that for those two, since our viewing angle distribution is non-uniform, so the MATE is slightly better than using directly applying graph Laplacian tomography. So the fourth column is using the expectation and maximization. We do 10 random initialization, and in this part, essentially we are doing iterative template matching and reconstruction. So for the last three columns, we are using GAN-based reconstruction. And for the given P column, we are basically providing the information of the distribution of the viewing angle to the network. So it's P is not optimized. And we can see that these are the reconstructed images. For the second to last column, we assume that P is uniform, which is a mismatch from the underlying true angular distribution. And we can see that the resulting images are worse than if you are given the correct P. So the last column is assuming that there's the distribution P is unknown, and we jointly recover C and P. And we can see that this can greatly improve the results, let's say from the second to last, where we fix P as uniform. So we can see that it is important to actually jointly recover C and P when P is unknown. So here we do another numerical test with signal to noise ratio is equal to 3. Here, signal to noise ratio is the variance of the signal divided by the variance of the noise. And so we can see that at very noisy case, pairwise comparison is kind of very noisy, so it's challenging to recover the underlying image. And then for the EM best random initialization, we can see that maybe in some iterations it gets stuck, and the resulting image is kind of blurry. And for the last 3 columns, still it's the same as the previous slide, and we can see that jointly recover P and C can greatly improve the results compared to if you have a misspecified distribution P. So in this last figure, for this part, we also show the comparison, the results of the estimated distribution. So the red curve is our estimation of P, and the green curve is the original P that we draw samples from, and the blue curves are the sample distribution. So for the clean data, we only take 2,000 measurements, and for the noisy case, we have 20,000 measurements. That's why you see that the blue curve on the left is more noisy compared to the green curve. Okay, so that's the end of the first part on the unknown view tomography. So now let's switch a little bit to the second topic, which is on the cryo-EM image denoising. So for the image denoising, let's look at the image formation model for this cryo-EM model. So basically, we have those hundreds of thousands of small molecules frozen in a thin ice layer. So we have those particles oriented at different poles. So we have, let's say, the underlying density map is phi, and we modify it through a group element xi in SO3. Then we do a linear transform, which is the tomographic projection of the underlying 3D volume. So for electron microscope, there's this point spread function where in the Fourier domain, it's called contrast transfer function, which modifies the frequency information by flipping the sign and also modulating the amplitude of the phase information. So the resulting effect from this original 2D tomographic projection with the CTF is the following. And then we also have, since we are imaging them with very low electron dose, so the resulting images are usually very, very noisy. So here I'm just showing you the simulated results for SNI is equal to 0.05 to 0.01. So you can see that it's very hard to visually get the information out of those images. So in addition, here I'm showing you a real data set that is downloaded from the website Empire Archive for cryo-electron microscopy. And I'm showing you 36 images for TRPV1 data set. So if you don't know the underlying images, it's really hard to really see the structures. Now, suppose I know the underlying 3D volume. I can generate templates through different projection directions. So on the right-hand side, I'm showing you if I generate templates and do cross correlation with those noisy observations, then these are the templates that best align with those or have the highest correlation with those noisy images. But the question is, can we identify the images, let's say, that are similar within those noisy observations and denoise the raw images without knowing this underlying true 3D density map? So, so the idea is basically in cryo-EM single particle analysis pipeline, there's a step called 2D class averaging, which aims at denoising the underlying those measurement data. So the idea is very simple. If you have images of very similar viewing directions, they might be different by some in-plane rotation. And once you in-plane rotationally align those images and average them, then you can increase the signal to noise ratio. The main challenge is really to identify images that are of the similar viewing direction. So using those denoise images, we can assess the data quality in general, and then we can also use those denoise images to do 3D ab initio reconstruction using methods like common lines or map estimation or method of moments. So to do this 2D class averaging, the first step is to evaluate the affinity or distance between images. And we call it rotational invariant distance, where basically for any two images, you do rotational alignment and find the best registration angle. Let's say alpha ij, we call it optimal alignment angle. So once you have those dij and alpha ij information for all pairs of images, then we can define a neighborhood graph where we connect node I and node J. So each node represents an image, and we can connect I and J if I and J are nearest neighbors in terms of the rotational invariant distance. And we can also associate the transformation information on the edge. So on the edge, you have the distance information and also the optimal alignment information. So the idea is now if we look at the data geometry, right? So here, let's say we simulate from this 3D molecule, and we can determine, say, viewing angle V1, V2, V3, V4 are very similar. So we plot those four images out, and you can see that they look very similar, but they are different by up to some in-plane rotation angle. And let's say for the image of viewing angle V1, we can introduce the local coordinates X and Y indicated in the orange. Then we can also say for viewing angle V3, we also have the local coordinates V1, like let's say this is X and Y. We can think about basically we have local coordinates on the sphere at viewing angle V3, and also a local coordinates in 3D at V1. So the idea is essentially if we have this optimal alignment angle, and if ij are very close, then e to the I alpha ij approximates the local parallel transport operator on the sphere, which basically transport this frame into from V3 to V1. So the effect is basically I'm now transporting this solid blue arrow into the local frame of V1. And then you basically need to rotate those two coordinates by this angle alpha ij. Okay, so now if we group all the images together, right? So based on the rotational invariant distance for the clean images, we can build a nice neighborhood graph indicated by those green short chords on the sphere. And we also have the consistency of the in-plane rotational angle for those connected neighbors. However, when we have noisy data, right? So here I'm showing you some images of, let's say, SNR is equal to 0.5. We see that sometimes maybe the rotational invariant distance identified that this image is close with this image instead of to its true underlying nearest neighbor. So we have those missing green dash line and also those short chords that shortcut the points on the two-dimensional sphere in the orange chords. So the noisy data basically induces the short chords on this geometric graph. And the question is, how can we remove those orange chords and then recover those missing green dash lines? So the overall goal for our initial 2D class averaging is how can we improve the nearest neighbor identification when the data is extremely noisy, right? So the overall pipeline for our denoising is the following. So we have those noisy data, we get those single particle images, we measure, let's say, the rotational invariant distance for pairwise images. Now we have those short chords where compared to if we have the clean data with the clean neighborhood graph. So using the method we developed called multi-frequency vector diffusion maps, we can classify or finding the new nearest neighbors and basically removing all those, most of those orange chords and identifying those true nearest neighbors. And we also improve the alignment in this framework. Once we have that, we can also reconstruct our graph for the images and use some kind of graph denoising techniques to denoise the images. So there are many techniques for manifold learning that we can use for this application. For example, locally linear embedding, isomap, Hessian, LLE, Laplacian eigenmaps, diffusion maps, and vector diffusion maps, etc. So here is just an overview of the results. So we have those noisy images, and previously we showed the closest match based on if you know the underlying 3D volume. And for our denoising algorithm, this the right-hand side is our recover denoised images from the raw data. So just to get to overview how we do it. So let's first review some of the techniques in manifold learning. We know like Laplacian eigenmaps and diffusion maps, basically first we build an n by n matrix, let's say W0, which is essentially equal to some scalar weights between node I and node J, which is defined as, let's say, exponential of minus and the rotational invariant distance between I and J squared over some parameter epsilon. We can identify the degree matrix of the diagonal degree matrix of W0. Then we can construct the graph Laplacian and the random walk matrix. Let's say L0 is equal to D0 minus W0, or A0 is equal to D0 to the minus 1 times W0. So the diffusion maps is defined in terms of the eigenvectors of this random walk matrix. And we have the eigenvalue and eigenvectors, and the diffusion maps phi t is a mapping for each node I to using, let's say, this the eigenvectors weighted by the eigenvalues. So once you have this mapping, the diffusion distance between any 2 points in the graph is essentially an L2 distance between your embedded vector. Okay, so basically we can, for our application, we can use our invariant distance and then using the diffusion maps to identify nearest neighbors. However, in this framework, we didn't really use any information from our optimal alignment angle. So the idea of the vector diffusion maps is to identify, let's say, for nearest neighbor points on the S2, the alignment should be cycle consistent. So meaning that if you know the optimal alignment between image I and J is alpha ij and J and L is alpha JL, then for any cycles, so here is a cycle of length 3, this summing over the angular transformation should be equal to 0 mod 2 pi. So in the vector diffusion map, essentially the idea is to quantify, assess if I and J are nearest neighbors by the consistency of transporting a unit vector through different paths underlying those angular transformations. And if these are consistent, then you have high affinity. If those paths are not consistent, then the resulting score is low. So you have low affinity. So instead of just summing over the weights of all the paths that's associated with the diffusion maps, the VDM sums over the transformations. Now, for multi-frequency vector diffusion maps, what we identify is essentially if you have any integer k for any frequency k, we should also constrain that k times this cycle consistency should be also, like, let's say alpha ij plus alpha jl plus alpha li is almost equal to 0 mod 2 pi. So instead of just having e to the I alpha ij, we can actually have e to the ik alpha ij. Right. So we can measure the consistency of the transformations at different frequencies. So in order to do that, we basically construct the matrix of the following form. So instead of just the scalar weights on the graph, edge weight, we also have this parameter that characterizes the transformation between node I and node j. Again, we can also define the degree matrix for each node by just summing over the scalar weights. And then we can define this averaging operator for the vector fields instead of scalar like functions. So this is essentially for each vector in 2D, you basically rotate it by this k alpha, and then you do the sum according to the scalar weights on the edge. So AK itself is not a Hermitian matrix, but it is similar to a Hermitian matrix by doing this additional weighting of our original WK matrix using the degrees of each node. Then we define the affinity between I and j using this a to the power 2t or a sub k to the power 2t ij. Okay, so therefore for a to the k, since it's a Hermitian matrix, we can compute its eigenvalues and eigenvectors. And our frequency k VDM is essentially using the corresponding eigenvalues and eigenvectors, right? And here L and R should be from 1 to n. So if you incorporate all possible eigenvectors, you can see that this vector is going to be very high dimensional. Instead, we can do a truncated frequency k VDM by truncating MK to MK, where MK is much, much smaller than n. So then our affinity between I and j is evaluated as the inner product of our truncated frequency k VDM map. In addition, the byproduct of computing the eigenvectors of those matrices A sub k is that the eigenvectors are group equivariant, meaning that if we rotate the image ij by an angle alpha, the corresponding eigenvector entries will be modified by this e to the ik alpha. So pictorially, you can see we indicate the top 5 eigenvectors evaluated at entries I and j. So the solid arrow are for I and the dash arrow is for j. So you can see that if vi is equal to vj, then those vectors in the solid is just in dash arrows is just the rotated copies, a copy of the arrows in the solid line. So essentially, the relation between the eigen entries in the eigenvectors is e to the ik alpha ij times ul evaluated at j. So based on this information, now it helps us to do another estimation of the in-plane rotational angles. So that is, instead of going back to the image and do another check of the in-plane rotation, we can directly use the eigenvectors to estimate the optimal alignment angle for any pair of ij. and it can be more robust than just going back to the image and compare the noisy images. So now for multiple frequency vector diffusion maps, we have different embeddings at different frequencies. We can combine those embedding vectors and have a joint affinity score by concatenating those vectors and normalizing them. So the idea is basically for each graph, you can have an affinity score, and based on like summing over those affinity scores, having a joint like voting can help us to have more robust estimation of the nearest neighbor pair. Okay, so for the time sake, I will skip this part and just tell you. So once we have the new nearest neighbor list, then we can try to use the eigenvectors of the new graph to denoise our images. So in order to do that, we also need to use this Fourier-Bessel expansion. And the reason is under this truncated steerable basis expansion, the expansion coefficients follow this following property, has the following property. So if you rotate the image, the expansion coefficients is just changed by this phase of e to the ik alpha. Therefore, for the 2D class averaging, we can basically apply our AK to the expansion coefficients B, and that gives us the denoised expansion coefficients. And from the denoised expansion coefficients, we can reconstruct the underlying images. And here to avoid over smoothing, we design a filter, which is like this 2AK minus AK squared. Okay, so now here I show you some experimental results based on the simulated data. So the first column is the noisy and the second column is the underlying clean images. And we have MFVDM, which is our result. And for MFVDM star, what we skipped one step, which is improving the nearest neighbor identification. And we directly use the old graph and the eigenvectors to filter the images. So we can see that this is slightly worse than if you can improve the underlying graph structure and the alignment parameters. So the others are the other baselines like Reliant and steerable graph Laplacian, covariance Wiener filtering, and our previous 2D class averaging method. So we can see that the MF medium, which improves the nearest neighbor search and alignment, and also use the graph Laplacian the eigenvectors to filter the images, has the best results for the denoising. And also our method is pretty efficient in comparison with, say, Reliant. So here we also apply our methods to the real data set where these data are downloaded from the Empire archive. So we show the closest projection images, and then the remainings are our denoised images. So overall, so in summary, we basically mentioned two applications in dealing with the imaging data from scientific applications. So we can see that using the MFVDM can improve our estimation of the nearest neighbors and optimal alignments from the noisy measurements. And also the eigenvectors can be used to perform nonlinear filtering of the cryo-EM images. And for the first part, we talked about using the adversarial learning to improve the reconstruction quality for unknown view tomography. So for the future, we want to actually extend that adversarial learning framework to 3D reconstruction. And we are also exploring what is a best and computationally efficient way to compare distributions in high dimensional space. And also we want to understand the sample complexity for noisy data. And moreover, we want to adapt this framework to more different like measurement noise model or uncertainty. What I mean by this is this part is a very flexible framework that can be incorporated in a like a lot of different imaging and inverse problem framework, where suppose your measurement has some underlying latent parameters that is unknown, or you don't really need to recover them, but the distribution of that might be more important, then we can use this framework to solve that kind of problem. Okay, so that's it for my talk. And I would like to thank all my students and also my sponsors. Okay, any questions?
Dr. Zhao, thank you so much. If anyone has any questions, please feel free to unmute and ask directly. What an interesting talk. And as a reminder for everyone, this presentation is recorded and will be on our website at ai.ncsa.illinois.edu in a couple of days, probably near the end of this week. If you would like to follow up with Dr. Zhao, please contact any of us in the AI Center, and we would be happy to put you in touch. Dr. Zhao, thank you so much for the presentation. Excellent. Really appreciate your time, and we will see you all next week. Thank you again. And again, that presentation on our website in a few days. Thanks, and have a great rest of your day.
Okay, thanks.